In this video, I'm going to be working some double integral examples that require you to reverse the order of integration. And this is multivariable homework 3.4. So we're going to start with this one. And the whole issue here is if I tried to anti-differentiate x times the square root of 1 plus y to the 3 with respect to y, well, I wouldn't be able to think of an antiderivative. Okay, so we're going to have to try something else. So always the first step is going to be over here, sketch the root, right? So I'm going to say, all right, I can do that. Y is running from y equals x to y equals 2, right? So I need to kind of plot those. Okay, y equals x, I know what that looks like. Y equals 2, say maybe it's right there. Okay. And then x is going to want to run from 0 up to 2. Okay, so that would be, right here, x is equal to 0. If y equals x, that's going to be x equals 2. So if y is between x and 2, we're talking about this region right here. Okay. But, we need to reverse the order of integration, so we want to write it as a double integral of x square root of 1 plus y to the 3. Oops, dx dy. Okay. So we need to start by saying what are the x values, right? Okay, we need to get some sort of x bounds. So x looks like it starts over here and it ends over there. Okay, this line, this y-axis here, this is the line x equals 0. And if this is y equals x, then we need to just solve for this x in terms of y, and that would be x equals y. Okay, so over here, I've got x equals 0. Over here, I've got x equals y, so I'm going to say x runs from 0 to y. And then y, I think that's going to need to go from 0 up to 2. And remember, our outside bounds of integration need to always be numbers. Okay, so now I'm ready, right? I'm going to try to think of an antiderivative for this with respect to x, and I can do that. That will be still integral from 0 to 2. 1/2 x squared, and leave this thing the same because it's a constant. And that says x runs from 0 up to y. And then we're still integrating that with respect to y. All right, when I plug in y, I'm going to get 1/2 y squared times the square root of 1 plus y to the 3rd. When I plug in x equals 0, I get all of that zeroed. So this equals the integral from 0 to 2 of, maybe I'll even factor out that 1/2. Okay, y squared times the square root of 1 plus y to the 3. Okay, now this is set up. I'm going to need to use e substitution here. So I'm going to say let u equal 1 plus y to the 3 so that du is equal to 3y squared dy. Okay, I don't have 3y squared dy, I just have 1y squared dy. But actually, there was some discussion. I was talking about some people in my class about this problem. And that 1/2 was kind of causing us some issues. So I think I might actually solve for 1/2 y squared. So if I divided by 3, I'd have 1/3 du, and that would be y squared dy. But if I want 1/2 y squared dy, well, that's going to have to be 1/6 of du, right? Because I started with 1/3 du equals y squared dy, but I wanted to divide both sides by 2. Okay, and then I'm going to need to change the bounds. So y equals 0 gives me u equals 1. And when y equals 2, that gives me u equals 9. Okay, so now, in dealing with the 1/2 and the y squared, that's become the integral from u equals 1 equals 9 of the square root of u, and 1/2 y squared dy is 1/6 of du. So I'll put the 1/6 here and the du over there. Looks like I'm going to need a little more room here. Shrink it down a little bit and say, all right, ready to go. this is, all right, u to the 1/2, I anti-differentiate, I get 2/3 u to the 3/2. Okay, I can factor out the 2/3, just let u run from 1 to 9. Okay, so this is 2/18, or 1/9, of 9 to the 3/2 minus 1 to the 3/2. Okay, 1 to the 3/2 is going to be 1. 9 to the 3/2 is the square root of 9, taken to the third power. So that's going to be 27. So this is going to end up being 26 divided by 9. Okay, the next one is the integral from 0 to 1, or the integral from y to 1 of sine of x squared dx dy. Okay, again, you try to anti-differentiate sine of x squared with respect to x, it's not going to go well for you. So we just need to sketch the region we're talking about. Looks like x is running from y up to 1. X is going from x equals y to x equals 1. Right? X equals y looks like that. And x equals 1 is going to be out here. Okay, so if x is between y and 1, we're probably looking at that region here. Let's make sure. And y, okay, and y, we are running from 0 up to 1. Yeah, that's y equals 0, that's y equals 1. Okay. So what I'm going to do is I'm going to say, all right, this is definitely the region I'm interested in. Right there. So I need to rewrite this with the dy and then dx order of integration. Okay, and so if I want to know about y, okay, here y is going to run from the x-axis, that's y equals 0, up to, well, this would be y equals x. So this is y equals 0, this is y equals x. And then x, okay, it looks like x is running from 0 to 1. Now I'm going to find an antiderivative for sine of x squared with respect to y, and that would just be sine of x squared times y. As y runs from 0 up to x, and we're still integrating that from 0 to 1 with respect to x. Okay, when I plug in y equals x, I'll get, might write it as x sine of x squared. I don't know, maybe that makes it a little easier for you to recognize. And then I plug in y equals 0, again the whole thing goes 0, so that doesn't really contribute anything. So I'm just integrating 0 to 1 on this thing with respect to x. Okay. And, okay, yep, I'm going to say, this is u substitution. I'm going to let u equal x squared. Du is 2x dx, so x dx, which is what I have, is equal to half of du. Okay. And I need to convert the bounds. When x equals 0, that gives me u equals 0, and when x equals 1, that gives me u equals 1. So this is now the integral from u equals 0 up to u equals 1 of the sine of u, and then x dx was half of du. So I'll put the du there and the 1/2 over here. And I'll say, all right, I'm going to find an antiderivative for sine of u with respect to u, and that would be negative cosine u. So I'll say that's negative half of cosine u as u runs from 0 up to 1. And that's going to be, pardon me, negative 1/2 of cosine of 1 minus, well, cosine of 0 is 1. If you wanted this to look a little nicer, you could call this positive 1/2 minus half the cosine of 1. And that would be an exact. Okay, another double integral, same issue. No antiderivative for e to the negative y squared with respect to y. Doesn't exist. So we're going to sketch our region. Okay, it looks like y is running from y equals x to y equals 2. Okay, so y equals x. I feel like we just ran this exact same region, but it's all right. This problem so it's a little repetitive with the regions. I might try to find a couple of more examples to do at the end of this video. Okay, so yeah, if y, the lower bound of the region is y equals x, and the upper bound is y equals 2. That's another way of looking at it. And then x runs from 0 to 2. That's here, that's there. Okay. Then I'm going to say, all right, it's definitely this triangular region. And I'm going to rewrite this. Oh, whoops. E to the negative y squared dx and then dy. Okay, so x is going to start over here at x equals 0 and go over here to x equals y. And then y is running from y equals 0 up to y equals 2. Okay. Now I'm going to, what am I thinking? Oh yeah, I'm just going to anti-differentiate with respect to x, which is just going to bring in an x because e to the negative y squared is constant with respect to x. So x e to the negative y squared as x runs from 0 up to y. Okay. Same exact thing's going to happen here. I'm going to end up with y e to the negative y squared dy integrated from 0 to 2, because when I plug in x equals y, I get y e to the negative y squared, and when I plug in x equals 0, I get 0. Okay, this is u du again. Okay, u is going to be negative y squared, so that du is negative 2y dy. Okay, I have 1y dy, so that's going to end up being negative half du. Okay. Need to convert the bounds. So x equals 0 gives me u equals 0, and x equals 2 gives me u equals negative 4, right? Because exponents before multiplication by negative 1. All right, so now this is the integral from u equals 0 up to u equals negative 4 of e to the u, and then y dy was negative half of du. Okay, antiderivative for e to the u with respect to u is going to be e to the u. Okay. And then that's going to be negative 1/2 of e to the negative 4 minus e to the 0. And again, I could distribute that if I wanted and say that's positive 1/2 minus 1 over 2e to the 4. Okay, and that's going to be a positive number like you would expect, integrating a positive function over, well, really any domain. Okay, number 4 is the integral from 0 to 2, the integral from y squared to 4 of square root x sine x dx dy. Pardon me. All right, and yeah, I think that the issue here is if you tried to use integration by parts on square root x sine x, it just wouldn't go that well. I don't know that it's impossible. It might be, though. I don't want to think too much about it. We're just going to instead trust that since this isn't a problem set that's talking about reversing the order of integration, that reversing the order of integration is going to be just right for us. Okay, and I think that'll be a good thing. Okay, so this one's going to be a little different, right? X runs from x equals y squared to x equals 4. All right, x equals y squared. You might not know how do I graph that? Well, you could say it's a sideways parabola, first of all, or you could just solve for y if that made it a little more familiar. And y would equal plus or minus the square root of x. Okay, so that's the square root of x. There's going to be another half of it down here, but then notice that x stops here at 4, so I should probably graph that. But y is only running from 0 to 2. So I've got here y equals 0, there y equals 2. So I know it's only that top half of that square root curve that I need. And the region we're interested in is this one. Oh, whoops. We know that we need to switch this to integrating square root x, sine x, dy, and then dx. Okay. We're going to need to get an expression for y. Okay, so y starts down here and goes all the way up to here. Okay, down here I've got y equals 0, and over here I've got y equals the square root of x. Interesting. Not sure how that's going to go, but I've got faith. X is running from 0 up to 4. Right. Oh, yeah, okay. It's going to be interesting. Okay, I'm going to take an antiderivative, and that's going to be, with respect to y, it'll be square root x sine x y. Pardon me. I'll write it like that. As y runs from 0 up to the square root of x. I'm still integrating from 0 to 4 with respect to x. Okay, when I plug in square root x, I'll have a square root x here and a square root x there. And that'll be in total 1 power of x. So I'll have x times sine x. And then when I plug in y equals 0, that will be, that'll make the whole thing 0, so it'll go away. And now I'm integrating from 0 to 4 x sine x dx. Glad I put this one on there. Didn't realize this one was going to require integration by parts. But it's good that you refamiliarize yourself with that. Okay. So I look and I see I've got x and sine x. I've got an algebraic object and a trig object. You think to yourself, I late. Algebra before trigonometry. So I'm going to let u equal x and dv equals sine x dx, meaning that du is dx and v equals negative cosine x. Okay. We know that the integral of u dv equals times v minus the integral of v du. Okay, so we're going to say that this integral is equal to u times v, so negative x cosine x, and we're going to need to evaluate that from 0 to 4. Why 4? Trig. I think we could have come up with maybe exponential or something a little better so we don't have to deal with cosine of 4, but it's all right. Not our problem. Minus the integral from 0 to 4 of v du. Okay, so since v is negative cosine x, that'll make that a plus. And du is dx, so cosine x dx. Okay. And we can do this. This is going to be negative 4 times the cosine of 4 minus negative 0 times the cosine of 0. Well, that'll just be 0. Plus, okay, antiderivative for cosine of x is sine of x. And I know that that will be sine of 4 minus the sine of 0. And we know sine of 0 is 0. So this is sine of 4 minus 4 times the cosine of 4. Well, I think that was a good set of 4 examples. So I'm going to call it for this video. I'm going to come back with a few more examples where you have to reverse the order of integration. But for now, this is going to be good enough. So thanks for watching.